So convergence is a very strict requirement because it says every element past capital N has to lie in this little window. Okay? And that's pretty strict. We might want to loosen that a bit to give ourselves a more general concept, the concept of a limit point. All right? So now we're going to modify the language slightly. Given any epsilon greater than 0, infinitely many values of n have a sub n minus L in absolute value less than epsilon. Right? So the concept is very similar to the concept of a limit. We again have capital L, our limit point now, on the number line. Again, we're given an epsilon greater than 0, which sets up a window around our limit point. But now, rather than saying there is a far enough down the sequence such that every element past that point in the sequence has to lie within this window, we don't say that. We say instead, infinitely many elements of the sequence lie in this window. Okay? And again, that has to be true regardless of how small the window is. That's what this verbiage here indicates. Given any epsilon greater than 0, infinitely many values of n have a sub n lie in this window. All right, so this opens the whole thing up. For example, we could have a sequence like this. A sub n equals 12 if n is even, and it equals n if n is odd. This sequence obviously does not converge. All right, it would go 1, 12, 1, 12, 3, 12, 5, 12, 7, 12, right? It doesn't converge. It's not even bounded. Bounded means that there's a number such that the absolute value of every element in the sequence is less than that number. Bounded. All right? This sequence isn't bounded. It doesn't converge. But it certainly does have a limit point. Its limit point would be 12. All right? So this sequence has exactly one limit point. We could easily modify it in such a way that it has two limit points. negative 2, 12, negative 2, 12, negative 2, 12, so on and so forth. All right? We could have another sequence that we give explicitly that also has 2 limit points. All right? This sequence bunches up around 1 and simultaneously around negative 1. The fact that these 2 limit points, well, the fact that there are 2 of them, implies immediately that the sequence can't converge, right? Because if it converged, that would mean that every element of the sequence past a certain point has to bunch up around a particular number. Okay? And if I have 2 limit points, then I have to have infinitely many elements of the sequence bunching up here and infinitely many bunching up here. Those 2 things cannot simultaneously be true for different points. Okay? So you can't have more than 1 limit point and still converge. That said, if your sequence has a limit point, then there must be a subsequence. All right? A sequence consisting of infinitely many terms of the original sequence, but maybe not all of them. And that subsequence will converge to your limit point. Okay? So this is this interesting generalization of convergence, this concept of a limit point. Now this gives us access to a very interesting result. Okay? A bounded sequence all right, so what does that mean? That means there exists a capital M such that the absolute value of AN is less than capital M for all N. It's bounded. Okay, a bounded sequence is one that has to lie on this interval of the number line. Every element has to lie on that interval. Now, if every element lies on that interval of finite size, and there are infinitely many elements, then what we can do is we can imagine, given epsilon greater than 0, breaking this interval on the number line into segments of width epsilon. Okay? There are only going to be 2m over epsilon of those little bins. 2m over epsilon. And that's a finite number because epsilon is greater than 0 and m is a number. Okay? So 2m divided by epsilon is finite. But I have infinitely many elements of my sequence, all of which have to lie on this interval. So since there's only a finite number of bins, and I have to dump infinitely many elements into those bins, at least one of those bins must have infinitely many elements within it. And this is true for any given epsilon greater than 0. So that implies that a bounded sequence has at least one limit point. All right? A bounded sequence must have at least one limit point. It might have more than one, but it has to have at least one. Okay? Moreover, if it's bounded and it only has one limit point, then it has to converge to that limit. Okay? And that's because if it only has one limit point, then there's only going to be one of those bins that contains infinitely many. All right? The rest of the bins only contain a finite number. So that means there must be a far enough down the list where all the rest of them have to fall in that one bin. And that means converge. All right? Now, just establishing that a sequence has at least one limit point is very different from actually finding a limit point. One example is given by this sequence. AN is equal to the cosine of n squared. Okay? And of course, we're working in radians. All right? So I would have cosine 1, cosine 4, cosine 9, cosine 16, so on and so forth. These are all irrational numbers. But this sequence is clearly bounded. All right, since no integer multiple of pi is a square of a natural number, cosine n squared can never be equal to plus or minus 1. So it's got to be bounded. That means we have to have at least one limit point for this sequence because it's bounded. All right? Now, often people think, oh, well, the limit points are going to be plus or minus 1. But it's a little bit more complicated than that. So let's go ahead and see what the elements of this sequence look like. All right, so I'm going to do a table of n, and then I need a numerical value, cosine of n squared. All right, I'm going to go ahead and give myself 5 digits. And let's look n from 1 to 10. All right, this, by the way, is Mathematica, which I'll put instructions as far as how you can use this program on your computer on Blackboard. All right? So we see here that the values of this sequence sort of jump around. We can go ahead and look at visually what these elements look like by doing a list plot. And we can see here that they're all over the place. It certainly doesn't appear to converge. I mean, they're just all over the place. So we can look at that. We know that there must be at least one limit point, but we don't know which limit points we can point out. In fact, it seems like every element on the whole interval is a limit point of this sequence. But stating that and proving it are very, very different things. All right?